Hey folks, how's it going? So we're looking at question number 12 in this chapter, and it's a weird one. It's more like a physics question than a question about limits. So I'm just going to solve part A because part B and part C they're pretty much the same, but with different numbers, right? But the process is exactly the same. It's barely even a process. Okay, so anyway, so what we have here is that we have the function for the velocity of a rocket as it goes away from a planet. All right. So basically, it's telling you what the velocity of the rocket would be given a few things, right? So v naught squared, that's the big one. That's actually the initial velocity of the rocket, right? And um, the small r here, that's the distance of the rocket from the center of the planet, and the capital R here, that is the radius of the planet. Okay, and m here represents the mass of the planet, and capital G is the universal gravitational constant, right? So again, it's they've one thing to note here is that it's not like a universally applicable formula, right? It's for their rocket specifically because apparently they've already plugged in acceleration and stuff like that off their rocket. I mean, or maybe it never had any anyway. But yeah, it's not like a universal formula. But what they want to tell you is that okay, as you go away from the planet, your velocity drops off as square root of your distance from the planet, from the center of it, and some change. So for planet Earth, they've already plugged in the values for these constants and given us this thing, the simplified equation. All right. So think about it. Eventually, right, as the radius goes up, I don't know why I keep calling it radius, my bad, it's the distance. As the distance of the rocket from the center of the planet goes up, the velocity goes down, right? Eventually, the velocity is going to drop to zero, right? And the rocket is going to start falling backwards and start, orbiting the planet. Or if it drops really quickly, it's just going to fall back on the surface of the planet. But yeah, so what it means is it doesn't really escape the gravitational field of the planet unless as velocity tends to zero, r tends to infinity, right? What does that mean? Once again, it means that we're looking for the case when the velocity of the rocket becomes zero or close to zero only when the distance from the planet tends to infinity, right? So is such a value of the initial velocity possible, right? Can we launch a rocket so hard that it just escapes the gravitational field completely? Yeah, we can, and that's called the escape velocity, v naught, right? So for part A, they just want you to find the escape velocity for planet Earth, right? So I think it's pretty straightforward. You can just say square root of 48, right? Because that would mean the velocity as a function of r is just going to be 192,000 over square root of r, right? Because these terms then cancel out, and you can rewrite the radius as 192,000 over v squared, right? So if you note, as v goes to zero, the limit of r, it actually tends to positive infinity, right? Because it's a squared term at the bottom, so it doesn't matter which direction we're talking about. But as this goes to zero, the distance from the planet that you need for velocity to tend to zero tends to infinity, right? Which means the rocket is never actually going to stop. It's going to just escape the field of the planet completely. Okay, so that's pretty much it. And the parts B and C of the same question, they just deal with different planets like the moon or some custom planet. Right? Hope that's helpful. Thank you.